Okay, hello and welcome everyone to today's midterm webinar about the ECMWF Summer of Weathercode 2022. My name is Julia Wagemann, and together with Esperanza Quatero, I'm the coordinator of the ECMWF Summer of Weathercode program. Today, we are presenting the midterm results of the 6 projects that have been selected for this year's ESOC edition. And we are really excited to have all the 6 projects with us, presenting their results so far during the coding phase. So just a bit of background about the ECMWF Summer of Weathercode. So it is a program that is running since 2018 and organized by the European Center for Medium Range Weather Forecasts together with the 2 Copernicus Service on Atmospheric Monitoring and Climate Change, which are also run by the European Center for Medium Range Weather Forecasts. And the program aims to bring innovation and open source developments to the Earth science community. And since 2018, each summer for 4 months between May and August, developer teams joined with ECMWF and Copernicus staff to work on open source developments and innovative projects. So since this year in May, since 2nd of May, the selected 6 teams of this year's edition are working together with the ECMWF mentors on their project. And so the coding phase is a 4-month-long period, and it will still last until the 31st of August. But today, because it's mid of July, we wanted to have or give an opportunity to also get a sneak peek on the current developments of all the projects. And so all the projects are open source, and you can also follow their developments on GitHub. If you go to github.com/esoc/challenges_2022. So today we have a full program. Each presentation has 15 minutes, so it will be around 12 to 13 minutes of presentation. And after each presentation, there's also room for some questions. And this is the overview. So we will have 6 projects presenting, and 5 projects are also with us today online and presenting live. And unfortunately, 1 team couldn't join us today live, but they prepared a very nice presentation, a video recording of their progress so far, which we will showcase, or which we will share with you also at the end. So this webinar is also for you. And so please, if you have questions on the projects and the results or the teams, or also in general about ECMWF Summer of Weathercode, feel free to go to slido.com and enter the hashtag ESOC 2022, or you can also scan the QR code here. And this is the room where you can, or this is the application where you can post your questions. And we will monitor this space. And after each presentation, if there are questions, we will directly address them. But in any case, we will also have some room right after the last presentation to address any additional questions that are coming in on Slido. And with this, I stop sharing my screen, and I would like to invite the first presenter, which is Adarsh Nagayan Pandey, to open the video and also to share the presentation. He's working on a project which is called ECMWF User Dashboard, which is a project that brings an existing prototype of a user dashboard closer to operations. So Adarsh, the floor is yours.
Can I get a quick confirmation that I'm visible and audible?
Yes, we can hear you and we can see you. Welcome.
Yeah, I'll share my screen. Is my screen visible to you guys?
Yes, we don't see the presentation yet, but yes, now we see it.
So, hello guys, I'm Adarsh Narayan Pandey, undergraduate at BITS Pilani, Goa campus, India. So I've been working on the user dashboard project as a part of Team 23 under ESOP 2022, mentored by Sylvia and Edward. So let's get started. The outline will be something like we'll go through the introduction, the goal of the project, quick revisit to the user dashboard that we had after ESOP 2021, the user dashboard V 2.0 as I name it, the architecture of the dashboard as it stands currently, the widget discussions, and followed by the demo and deliverables achieved, and then the future plans followed by the questionnaire. So, introduction. So ECMWF consists of a large user base spanning across the researchers and scholars that have data needs, and they can in turn ECMWF has a lot of applications and sub applications that cater that those data needs of the users. But till now there was no like central place to look out for the requested data. So if let's say you want to request data from 5 applications, you'll visit each application separately and look out for the status of your request and all. So to solve this issue, user dashboard was proposed as a project in 2021 which is being carried in 2022. So the goal of this project was that the follow-up of 2021 was that we had some basic architecture that allowed some apps to be connected to the dashboard. However, the need was for any app to be there as per the user's wish. So that was the main highlight of the challenge. And the goal was to move forward with integration from individual apps using simple discoverable widget API, comparable to get capabilities of OGC web services. We'll be going through all these things in the presentation, so don't worry if you don't understand some things right now. So quick run through of the application before ESOP 2022 coding phase. So this is what the application looked like. We had a nice dashboard, a chart browser, and which showed some iframe charts that could be added to the dashboard. Add widget menu bar which shows the types of widget that could be added, and as we can see they are kind of app specific. As of now they were kind of app specific, and then the tabs which could present the data as little application widgets. So current status is this is how it looks like. We'll go through the tech stack first. So it's built using TypeScript language. Backend libraries and frameworks are Node.js and Express.js. Frontend, we are using React, Next, and Markdown to JSX. Database tools and libraries are MongoDB and Mongoose as a library to query the MongoDB queries. API handlers, we are using Axios, and authentication, we are using Passport.js. So the architecture. So we had to define something API that can take any kind of app from the user and render it to the dashboard depending on the fixed types that we have. For that, we needed some endpoint that will list all the widgets according to the endpoints that will be provided to us by the ECMWF web team. So this get widget API is the endpoint that is responsible for listing out all the available widgets that we have and that can be added to the user dashboard. The response is of the following type. We'll have name and endpoint of the request that we get, and then the widgets will be listed as kind of the data, the payload that will be rendering on the widget browser. So this is how it happens. The widget browser sends a GET request to the user dashboard backend. It in turn sends a GET request to ECMWF get widgets endpoints, which gives us the data to the backend, and then the data reaches the widget browser, and this is how it is rendered in the front end. Behind the scenes, what happens is when we click to the user dashboard, it creates a GET request to the particular widget API, which after extracting the title, href, name, app URL type, and all, and making a config object of it, and it passes to something which we call as a tab manager. And then tab manager is responsible for adding this to the current widgets of a particular tab. Then the tab manager on like clicking the dashboard, the tab manager according to the type of the widget calls the widget builder builder's build function, and which in turn calls the widget blueprint, which is responsible for rendering the final data. So how widget blueprint works is it sends a GET request to the application endpoint, and it just like renders the UI. So we as of now have 4 different widget types, and any application falling in those 4 different widget types can be added to the dashboard, and it's not user specific. So that's like one of the biggest achievements so far. So we'll go through the widget types in brief. Table widgets are for rendering any kind of tabular data, allows that color coding according to the CSS colors based on the API response, which was not there in the previous version. And it is not specific to the application, but to the type, as I mentioned before. And this is how the API response of a table widgets is expected. We'll have some metadata, and then the table, the final data that we want will be an array of arrays. And then the styling is also important here, because this is how we'll be rendering and applying colors and some helpful stuff. And this is how the final UI of a table widget looks like. Next, we move on to the text widgets. These are for the textual data and has the ability to process markdown tests and convert accordingly. So this is how the API response of a text widget looks like. We'll have some metadata, and then the data is that we'll have something like this, markdown or static text, and then that will be rendered like this. Now we'll have iframe widgets. So these widgets can be used by any application that wants to provide a rich user interface through a widget. And again, it's not specific to the application, but to the type. So a typical iframe widget API response should look something like this, some metadata, and then we'll have the SRC in the data, and that points to the URL of the site to be displayed as an iframe. So iframe widgets are rendered something like this. Now it's time for a quick demo. I'll just give me a confirmation if you guys can see the dashboard application.
Yes, we can see it.
Yeah, so this is how the landing page looks like. We go to the user dashboard. Yeah, I'll just remove all these and add ones to make sure you guys get the view of what's happening. Yeah, so the widget browser is the one that is responsible for listing all the available widgets. Yeah, so we have the widget browser and with the toggle functionality for applying the images. Then we'll just add some of the widgets right now. Let's go to the dashboard, and yeah, you can see the different types of widgets on the dashboard. So this is a table widget with all the styling that has been specified by the application. These are the markdown widgets, and these also have clickable links. And then the OpenIFS widget for, again, which gives us a tabular data which is color coded according to the status of the request. So that's for the demo right now. I'll switch to the presentation. Now the deliverables that have been achieved are, like we discussed and formulated the API format for Git widgets and different application widgets. We created the widget browser, which was not there, a central place to explore and available application widgets that can be added to the dashboard. We transformed the architecture of the project from a centralized widget management tool, as we saw that we could query some widgets and add to the dashboard, to a place like to a generalized widget API, like from a central place to access data of different applications to a client application for different applications. Added a redirect button to redirect the user to a particular application for more information. added a refresh button in appropriate widgets, added main types of application architectures and rendered them successfully as widgets in the dashboard, allowed a markdown-based data rendering through text widgets, enabled custom styling in table type widgets according to the application's need to give visual representation of the type of data on the dashboard, accommodated chart widgets as iframe on the dashboard, and can render any application data as widgets on the dashboard that fall under those types. So what's next? The next phase of this coding period will focus more on adding more types of the widgets, implementing the filter functionality in the widget browser, which might include tag-based filtering and type-based filtering, code refactor, and more towards deployment, user authentication to retrieve personalized information from the widgets, and managing the state of application through user authentication context. So that's all for my presentation. If you have any question, you can just unmute yourself or write in the chat box.
Okay, thank you, Adarsh, for sharing these great results and also all the things you already did for the past 2 months, and also the plans you have until the end of the coding phase. So there are no questions yet on the Slido, but I have a question on your experience so far during Summer of WeatherCode in the last 2 months. So on a scale from 1 to 5, how challenging was so far getting started with the project and also implementing the results you did, or getting that far? How challenging on a scale of 1 to 5?
So I mean, it was new, so definitely was some there were some challenges at the start, and we had to go through what's already have been done, and then discussion on how to format the API responses and how to format the data. So these all took a lot of discussions with Sylvia and Edward, and then finally coding up these integrations required going through the large code base that we had. So on a scale of 1 to 10, my experience with the mentors is 10, because they were there whenever I like needed any help. Working on the project was quite exciting and challenging. So out of 5, I would rate it somewhere around 4, because I got to learn a lot of things and that I didn't know beforehand, and to be able to like do them successfully is like what made it great for me.
Okay, great. So we actually also have a question now on Slido. So the first one is also a compliment. So the user dashboard looks fantastic. Was the authentication a challenge?
Yeah, so authentication as of now is we are not currently allowing the like like we aren't currently offering that functionality yet, but it is there in the suite. We just haven't like tested it like extensively, but it's there in the suite. We have some parts of it like in the shared dashboard, which I'll be taking up the like in the next like moving forward in the next phase.
Okay, great. So thank you, Adarsh, for presenting today your midterm results and also being with us today. It's highly appreciated. So thanks again. Now I would like to present you or invite also Ali Shtipani to open his video and also share the screen. He's working on a project with the title Bringing Magic's Weather Maps to Matplotlib. And this project aims to integrate ECMWF's visualization library Magix to Matplotlib. And he will share with us how he plans, or he's doing it. So welcome, Alish, and the floor is yours.
Hey, Julia, thanks a lot. Ruben, could you share your screen?
Yes, I'll do it right now. Let me put the slides in presentation mode. Okay.
Yeah.
Can you see it?
Thanks a lot. I can see it, yeah.
Fantastic.
Thanks a lot. So, hey everyone, I'm Alice Tepani from India, and I will be talking about my ESOC 2022 project, bringing Magic Weather Maps to Matplotlib. And first of all, I would like to thank my mentors because this wouldn't have been possible without their support, James, Sylvie, Stefan, and Badovin. So next slide, please. So just to give an outline of how this talk will go, is that first I'll introduce what the Magics and the MacPy libraries are. Then I'll just give some examples about how it looked before the start of the project. Then I'll explain the motivation and the aim, the roadmap, the current progress, the challenges I faced, and what's next. So next slide, please. So to introduce, Magics is a meteorologically oriented graphical library, which was written using Fortran and C++, and it is responsible for visualizing meteorological data on different projections of the globe. So you could take any projections of the globe. Maybe you would like to present the weather of Europe, or maybe Asia, or maybe the whole world together. So Magics gives you the option to take some predefined geographical area and present any weather maps that you want to it. This could be something like a heat map about how the temperature is, or maybe how the wind is flowing, things like that. But this library was written, I think, way back in 1998, and this was written in Fortran and C++. But nowadays, the most used library is Python. So we would like to port this and add functionality so that users can interact with Magics using Python. So next slide, please. So that's why two new libraries were introduced. One is Magics Python and one is MacPy. So what Magics Python does is that it interacts with Magics so that you don't have to interact with it, and basically convert all the things into Python. And finally, we have MacPy, which sits on top of Magics Python and provides a very easy to use user interface to the Magics and Magics Python libraries. So the way in which this works is that you could give it input to a grep file or a netcdf file and the arguments that you want. You give it to MacPy, which passes it through which basically creates a geomap object. This then passes it through the Magics Python library, which creates a macro object. This macro object is responsible for communicating with Magics. Now you give everything to the Magics plots everything and gives the output in a binary format. Now we need to decode this binary format so that we could bring that to Python and Matplotlib. So the binary driver that is there in the Magics Python is responsible for this conversion, the conversion of binary format to a Matplotlib and a Python format. So this Matplotlib format file or object is passed to the geomap object, which gives us the output. So you could do many things with the output. So you could either print it and visualize it in a Jupyter notebook, or if you want to save it, you could save it as a PDF or a PNG file. So yeah, next slide, please. So an example of this was on the right side, you can see how Magics works. So it displays a very pretty figure, but while converting everything to Python, there are some steps which need to be taken care of. Things like aspect ratio, things like the width of the line, and also making text pretty and stuff like that. So before starting off the project, the right side example is what Magics Python looked like. So we wanted to make it pretty and also customizable. So next slide, please. So the motivation of this project is that we allow the user to take full control of the library and full control of the plot. And we wanted to make the plots more customizable and interactive so that user can define anything and manipulate the plot in any way that they want. And we also want to provide an easy to use interface for the users. So the first motivation is driven by the Magics Python library, and the second is the MacPy one. So in terms of the aim, so our aim is that we extend the binary driver to convert the binary format into Matplotlib access. And then we extend the MacPy to handle this Matplotlib format and provide an easy to use Pythonic interface. And finally, we plan to add the documentation and also the tutorial so that anyone and everyone could get started and even get into advanced about how to use these libraries. Without having to figure out how to actually interact with the Magics library, which is written in Fortran and C++. So next slide, please. So to explain how this roadmap looks like, so the first part is actually converting the binary format into the matplotlib format, which is handled by Magix Python. So the first part is improving the Magix Python, which encompasses making the binary driver matplotlib compatible, passing custom matplotlib access, adding color bar and stuff like that. The second is the improving MacPy to make MacPy actually matplotlib compatible again, so that the binary driver could convert the binary file into a matplotlib file and then allow the user to interact with it. And also the conversion of Magix coordinates to matplotlib coordinates, because the coordinates in these two systems are very different. So we need a way to convert and go forward and backward between these two coordinates as well. And the final is creating tutorials so that any user could get started. So we would create like beginner tutorials as well as advanced tutorials so that anyone could get started and use the library. So next slide, please. Yeah, so to talk about our current progress, so the first part that we achieved in the first half is improving the Magix Python. And the second half, will focus more on MacPy and creating the tutorials. So the updates till now is that we have updated the documentation. We have made the syntax more Pythonic for Magix Python. We took care of the aspect ratio. We improved the text. We improved setting the plot limits. And we also added passing custom matplotlib access to the Magix Python library so that you could pass something which is defined in matplotlib. You could just plot the Magix plot on that axis and customize it and do whatever you want with it. And we also added a color bar to it, so for better visualization. Next slide, please. So just to give a demo and just to give an example about how the aspect ratio, the improved text and the setting the plot limit looks like. So if you see the plot on the left side, so before the plot which I had shown before, so it had some text which did not have transparent background and it was overlapping with the figure. So right now we took care of everything. So we forced the aspect ratio to be equal because we wanted to be geographically accurate so that nothing is stretched and the sizes could be scalable. So we took care of the aspect ratio. We improved the text so that it does not overlap with the figure below that. And we also improved the setting the plot limits so that the figure looks pretty overall. And it's also geographically accurate. Next slide, please. So the next thing was to pass a custom matplotlib access. So by passing a custom matplotlib access, that means that we could plot, basically we could pass any matplotlib access. So let's say you want to make 4 figures at once. So this was not previously possible, but right now you could just pass, let's say a subplot of 2 cross 2, a matplotlib subplot, and you could plot different plots on that. So I saw an example on the left in which I basically created 2 subplots, and on one of the plots, I plot a Magix graph, and on below that, I basically plot a simple scatter plot. So you have the current hold of the matplotlib access. So you could say you could convey to Magix that just plot on this subplot, and you could do anything with that. So this basically makes the plots more customizable so that you take control of everything. Next slide, please. And finally, we added the color bar. So the color bar is there for visualization. So let's say you wanted to plot the temperature and you wanted to see how the temperature varies according to the geographical area. So on the top, you see the color bar plotted by the Magix library, which is discrete and overlaps with each other. But on the right side, you see the one which is in matplotlib. So what we do is we basically take the metadata being passed by the binary format. So we take that metadata, we basically use it to figure out how the colors look. So the metadata basically passes the legend, and the legend has the RGBA colors and the limits. So maybe this temperature is there, this color is there from -35 to -30 degree, and something is there from -30 to -25 degrees. So we take that, we basically create an image from that, and we append that image to the Magix plot. This is advantageous in the sense that we don't have to actually change the size of the plot. Whereas if you see the Magix color bar, it actually shrank the plot a little bit. But right now, we just append an image to the Magix plot so that the aspect ratio is not disturbed. So this color bar on the right, it looks pretty, and it is fully customizable. So you could you could basically manipulate it to set it to anything you want. You could say that you want a continuous color bar, or you can say that I want only these sticks in this color bar. So everything is customizable. Yeah, next slide, please. So this has been the progress till now. And so we have taken care of conversion of the binary format to the matplotlib format so that everything is customizable. Now the next part is to actually improve MatPy and to create tutorials. And by improving MatPy, we make sure that you don't have to know everything going on in the Magix backend. You just have very simple to use user interface, and you just say that maybe set this, set that, and rest everything MatPy and Magix Python will take care of it. So first of all, we need to convert. So to actually combine these figures, that is, let's say you wanted to plot a Magix plot, but you also wanted to create a scatter plot on top of that so that you could mix and match different plots. So the first thing that we will tackle is conversion of the data from Magix coordinate to matplotlib coordinate, because these are two separate coordinates. So if you have a data point in the Magix coordinate, you need to convert it into the matplotlib coordinate. And the second thing is making MatPy actually matplotlib compatible so that it could process the matplotlib format file, and you can show it, you can manipulate it, and you can do anything you want with it. And we also plan to add documentation and create tutorials, as I said, for beginners as well as advanced users. Yeah, thank you. Yeah, I'm open to questions.
Okay, thank you, Alish, for this great presentation and also these great results you already achieved so far. Again, also, I have to question to you, so on a scale from 1 to 10, how challenging were the two first months of the coding phase for you?
Yeah, so I think my experience has been really great. The mentors are really supportive and are there whenever I need them. So I would say on a scale of 1 to 10, the challenge has been around 8. So I knew how to work with matplotlib before. I knew the internal workings of the library, but interfacing it with the actual Magix library has been a challenge. And my mentors are really supportive in that case. And we discussed together to how to basically coordinate between the Magix and the matplotlib things. So it has been challenging, but the experience has been great.
Okay, yeah, so it's usually also if there's challenges, then there's also a learning curve behind. So there's one question also on Slido. So first of all, also a compliment, great presentation and great work, Alish. So what was the hardest part thus far in adapting the existing ECMWF libraries?
So I think the hardest part was the color bar, because the way in which it works is that Magix has its own coordinate system in which it works. And actually passing this, actually we had to figure out how to bring these coordinate systems to give that as metadata to matplotlib and actually plot that in matplotlib coordinate. So what we do is we take those coordinates that are in Magix coordinate, whatever coordinates that may be, then we basically take that as metadata. We need to process them so that matplotlib can understand that and plot it at correct points, and basically then plot the color bar. So I think color bar has been the most challenging thing right now.
Okay, so thank you, Alish, for the presentation and also for being with us today during this midterm webinar. And so now I would like to invite the Akshay Verma to open the video and also start sharing the screen. He works on a project with the title Climate Lab Web Application, and this project develops a graphical user interface to better utilize Climate Lab's features. And Climate Lab is a Python library also developed by ECMWF. So Akshay, welcome, and the floor is yours.
Thank you. Hello, everyone. My name is Akshaj, and today I'll be taking you through my work on the Climate Lab web application as part of this ESOF 2022 Summer of Code. So today I'll talk you through the motivation behind building this project and the solution which was proposed, how I built that solution and the features that I built with that. I will also show you how the user interface looks like right now and share with you my current progress and the next steps. All right, so the problem. So as of now, Climate Lab settings are configured via the terminal, which is cumbersome to use. Because first of all, you need some exposure to the terminal and how to use it. You would have to remember the features provided by Climate Lab's command line interface. Searching for files would require multiple keystrokes and typing often the same commands over and over with some small modifications. Deletion, especially batch deletion of files, would be difficult. And finally, viewing some of the statistics, such as the cache size or the number of cache files, that would require a repetitive entry. So the proposed solution to that would be building a graphical user interface. So while command lines are extremely helpful and often necessary for many edge cases, GUI for the most part smoothens out commonly used features that are used over and over. So in case of Climate Lab web app, a GUI will provide an easy method to search for files based on different characteristics, such as the file name or the file size, the date of creation. It would also display all available features on the screen. So you wouldn't have to refer to the documentation over and over again. It's easier to pick up compared to a command line and involves less typing for repetitive tasks. So now that we have that, let's look at how we architect this application. So on the left, you can see the front end, and on the right, you can see the actual Python package. And there's a reason that these two are decoupled. That's because we wanted the end user to have zero JavaScript dependency. And we achieved that by directly serving the HTML files via our backend in Flask. That's written in Flask. So how it works is on the left, we use React along with TypeScript to develop this app. We use Tailwind to style it and make reusable components out of style components. So after developing the app, we create a build output, which consists of all the HTML, CSS, and JavaScript, and copy that into the Climate Lab script web's root, which is then served by Flask. So in the end, the user will not have to download Node.js or run any Node server at all. We could simply just download this from PyPy and get working with it. And there's an additional dependency with Climate Lab. That's because we use certain features for filtering via the Climate Lab Python package. All right, so now that we know how we are building this, let's look at what we are building. So there are two main verticals, cache and settings. Settings would control the global behavior of Climate Lab. For example, it could mean setting the directory in which your cache files are downloaded, or it could mean different plotting options that you want to set. The second vertical, which is the cache, that involves two major features. One set of features could be clubbed under inspection, cache inspection, and the other under management. When we talk about cache management, that involves deleting the files, either single files or batch deletion, as well as setting the auto deletion policy. Inspection, on the other hand, that refers to the filtering of cache files. We talked about that earlier based on the file name and the file size and the dates. Having a disk usage overview that could show you how much size the cache occupies in your system, how many files are there. And finally, a preview where you could click on a cache file and a pop-up would just open and show you what that um, Grave.hdf file looks like. All right, moving on to the user interface that I've designed. So this was designed originally in Figma. It started out from small wireframes to what you're looking right now. So the UI is divided into two major parts, two major components, speaking in React terms. The one is the header and the second one is the table, the body. The header consists of the forms that we need and all of the input fields, and the body contains the table. So how this all works is I maintain a global state in the cache component that is updated based on the response from the server after we send them the search parameters. And then once that state changes from the server's response, all of the other components that depend on that state update themselves. In this case, the table depends on that cache data to render all of the rows that you see. So that updates. This is a second view of that same file, and it's just to show how the date and the file size work. So it's not the typical datetime format that you are used to seeing when you think of calendars on web browsers. So here we have created this input that's specifically based on Climate Lab's Matcher functionality that I will be talking about in the next few slides. So all of this is built using reusable components. The input fields, the drop-down, the table, everything. And that makes it easier as the project goes further along to develop new features and ensure that functionality and style-wise, things remain consistent. And finally, this is the final page, the settings page. This again would reuse the table component that I created earlier. And it's used to, again, set certain values that control the global behavior of Climate Lab. Right, so now that we've seen the UI, let's talk a little about the current progress. So as of now, the cache inspection module is almost complete. Most of the things are there. The filter functionality, which is the crux of the project, that's handled by the Matcher class in Climate Lab. And this Matcher class, oh, and by the way, none of the filtering functionality is written in JavaScript or even in Python inside this Climate Lab script. Right? All of it's being written and used from the Matcher class in Climate Lab. And this is to ensure that these features have a single point of origin and are easy to maintain, support, debug in the future. So this Matcher class, it expects a dictionary where the keys are what you see on the screen: match, larger, smaller, newer, and older. And all of them expect certain values. For example, if we talk about the dates, the H and D that you see correspond to the hours and days. You could also have M for minutes and S for seconds. If we talk about the file size, U, C, G, and K, there's also an M. They stand for gigabytes, kilobytes, and megabytes. And finally, the match, where you enter any text and it would recursively search for this text present in the cache's metadata. And I've created a small GIF of the current working functionality. And as you can see, it's easy to select or deselect files. It's easy to enter search terms, set the file size, including the values or the units. And then once you press apply, voila. All right, so now that we've covered all of that, let me tell you what my next steps are. So the immediate next steps would be to finish the cache page by adding a preview button and adding a new input, which filters by date. Then I would start working on the settings page and eventually the documentation. This is a rough timeline of the things. So on the left, things are completed in May and June. Green is the current month, and the future would be August. Thank you for listening in, everybody. Please let me know if you've got any questions.
Okay, thank you so much also for sharing your presentation and also results so far. I also have the question to you. So on a scale from 1 to 10, how challenging were the first 2 months of the coding period?
The first 2 months I feel were fairly challenging, but it was more to do with how we architect this application and how we design the APIs. There was more on the software design part rather than the actual the technology part, because we wanted this to be as easy to maintain so that in the future maintainers could modify something without having much difficulty.
Okay, so it looks already very promising, and I can't wait also to see then the final result in September. So thank you again for joining today and also to be with us today. And I would now invite Fiona Spuler and Jakob Wessel to open their cameras and also to share their screen. They're working on a project called Adjusting Climate Projections. And in this project, they're developing a software package that allows users to apply bias correction of climate models. And yeah, welcome Fiona and Jakob, the floor is yours.
Muting is good. Okay, so hello everyone. My name is Fiona, and you'll also meet Jakob, who I'm working on this project with together in a second. And like it was just mentioned, we're working on developing a Python package for the bias correction of climate models. And we want to start this presentation by motivating our project and motivating why we need bias correction and what bias correction is. So we all know that climate models are really important tools to understand future states of the climate and also to provide the basis for studying impacts of climate change on human society and ecosystems. However, climate models, especially sort of global general circulation models, have trouble representing a lot of processes. So this could be processes that occur below grid cell resolutions such as convection, but also, for example, land-atmosphere interactions are an active area of research. So because of this, because different climate models solve these challenges differently, climate models disagree on, for one, changes in important variables such as precipitation. So here you see a figure from the IPCC report where all the shaded areas are areas of low model agreement, which you see is sort of covers large parts of the Earth. And then also, not only that, but also for present day climate, models have trouble reproducing the statistical properties of variables. So here you see a comparison of the pattern correlation between different iterations of the climate model intercomparison project. And you see that for variables such as near surface air temperature, the correlation is quite high, but for other variables such as precipitation or soil moisture, it's quite low. So we can conclude that climate models are incredibly important, but also that they disagree and are biased and therefore require maybe some post-processing before being used in impact studies.
Hey, I'm Jakob. The definition of a climate model bias is that it is a systematic difference between a simulated climate statistic and the corresponding real-world statistic. For example, here we see a figure which is the bias in hot day probability. And we see that from true climate models, we see that over Austria, there's quite a significant bias in either of the climate models and in either direction. There are several ways to address this mismatch. One is to develop better climate models, and there is a lot of research on that. And another one, given that we don't want to maybe wait for the development of better climate models and we want to do impact studies now, is to bias correct existing models. Bias correction, the idea or the definition is that it's a post-processing step where an empirical transfer function between model simulations and observations is calibrated and applied to the climate model in the time period of interest. There's a variety of bias correction methods, and the literature for that is super rich. One of the most straightforward examples, I think, is linear scaling, which just calculates the model bias in the mean and the variance, and subtracts or divides this bias from future simulations. So we look at the difference between the calculated mean from the climate model over a historical period between the observed mean, and we subtract this bias from the future simulations. There is quantile mapping, which is one of the most prevalent methods, which calibrates a quantile by quantile mapping of simulated and observed distributions. So we look for the future methods, we look at which quantile is this calculated value, and then we map this calculated value onto observations. There's a graphic on the right which kind of illustrates that, but also many other methods, quantile delta mapping, equidistant CDF matching, just to name a few. Generally, one distinguishes between trend preserving and non-trend preserving methods. And one of the most often used methods is the so-called ECMIP3B methodology by Lange 2019, which is a parametric quantile mapping that is trend preserving or approximately trend preserving in all quantiles.
So we've seen that there's a variety of different bias correction methods to choose from. However, there's also some caveats that come with all these methodologies. And without wanting to go into too much detail in this brief presentation, I just want to highlight some points made most predominantly in the Marron 2017 publication that we thought about a lot when developing this software package and approaching this project. So a basic problem with bias correction is that it's prone to misuse. So in the paper, they show that sort of with this calibration, by calibrating an empirical transfer function, you can basically bias correct anything onto anything. So they show you can calibrate, you can bias correct temperature in Europe based on sort of precipitation in Australia or something sort of absurd like that. And that typical cross-validation cannot identify the improper use of bias correction. And that's because there's sort of no one-to-one correspondence between observations and climate simulation, but you can only look at sort of the distributional properties. Then the second point is that sort of if you put a bad model in, you'll still get a bad model out. So there's some sort of processes that a climate model might get wrong that won't be corrected through bias correction. And that's, for example, the placement of large-scale circulation patterns or the sort of regional responses to these large-scale patterns. And also, as briefly highlighted before, sort of there's the question of whether or not to preserve the climate change, the trend in the climate simulated by the model, based on whether you consider that trend to be credible. So what does this mean for applying bias correction? This means that for one sort of careful choice of climate model has to be carried out. Then that when evaluating the performance of bias corrections, methods that mainly sort of work on a location by location approach, that you need to evaluate the performance of these methods going beyond sort of marginal properties. And then also that some decision making on the side of the user is required depending on the impact they are interested in, and that therefore bias correction can't be considered a one-size-fits-all approach.
Based on this, we have identified three main issues and aims that we want to address in our project. The first is the lack of flexibility in existing software packages. Many existing software packages for bias correction implement one methodology. They fix a lot of methodological choices like distribution, smaller methods, and easy experimentation, also because of oftentimes questions of data formats, isn't really possible. So it's difficult to choose the most suitable method or the most suitable bias correction method for possibly a region, for a process that we want to debias, for kind of the problem at hand. So we want to develop a software package that allows easy experimentation with debiasing and allows flexibility in data formats. Secondly, bias correction oftentimes performs better for some variables than others. For example, precipitation extremes are often not well captured because the tails of precipitation are quite heavy. The distribution used in parametric quantum mapping might oftentimes not be the most suitable ones. And we want to implement some more recent methods based, for example, on extreme value theory, on some other papers to address these issues building on the ECMIP approach. And third, there's the need for process-based evaluation. So we want to integrate and evaluate an evaluation, or integrate and develop an evaluation framework that evaluates beyond marginal aspects to help users to first assess whether certain weather types, large-scale phenomena are captured well. And secondly, to evaluate the specific variable of interest in the climate-driving climate model before and after bias correction. So to get an assessment of the skill of a bias correction method and of the bias-corrected climate model, to get a feeling which bias correction might be appropriate, which one might not be. So we present to you iBias, which is a software package for the flexible and easy to use application and evaluation of bias correction. And we're going to lead you through some of the things we've implemented so far. And going to switch to a notebook,
I can
which
share.
is always a risk.
Yeah, one moment.
So this is just a small notebook illustrating some of the things we have implemented so far. The status we are currently in, we're going to focus on temperature here because temperature is always an easy case. We have currently implemented 6 different possible debiasing methodologies, excluding the ECMIP approach. ECMIP currently works except for 2 variables, which still require small adjustments. Furthermore, we are able to test certain assumptions that users might test that analyze certain debiasers. And we have implemented some kind of evaluation for evaluate the bias-corrected climate model. Just to lead you through part 1, given that I have a debiasing method that I want to apply, every debiasing method has certain assumptions. Those might be some kind of distribution that we assume might fit well. That might be some kind of stationarity assumption, some other things. And the first step in applying debiasing might always be to test these assumptions. So we have implemented, for example, goodness of fit tests. We can see an AIC, which is a model information criteria, to see whether it fits well. Or we can, for example, get out an histogram of how the distribution looks like and what distribution we would like to fit. And for example, here we see that the normal distribution, which is an often made choice for parametric quantum mapping, doesn't really fit well the temperature at the location we might want to debias it. We can furthermore look at residuals of fits we want to put in to see, for example, that we have a lot of seasonality inside the residuals. So in some parts of the year it fits better, in some parts of the year it doesn't fit better. And once we have looked at those assumptions, we can initialize and apply debiasers. Here we just show some forms of initialization. We initialize, for example, a debiaser, quantum mapping debiaser for temperature, where we want to look at an additive bias. We can apply this onto a future period and onto a historical period, so a reference period. We can do the same thing with ECMIP. And also just down there, we're shown some of the other debiasers we've implemented, for example, delta change. We can implement quantum mapping for a temperature variable with different distribution or different delta type. So there's a lot of flexibility on how users might want to specify their debiasers and might want to switch out certain methods to test whether something fits better or fits worse. And then once we run this, we can, of course, evaluate the bias-corrected results on some sort of validation period.
Okay, and just sort of for this demo, we just picked some evaluation metrics that we've implemented to sort of show how they can help you assess which bias correction method to use. So what we do here in this part is we have initialized our debiases, and now we compare the raw climate model, so the biased climate model, with the debiased climate model using different methods. And here, sort of to illustrate, we use quantile mapping, abbreviated with QM, and ECMAP, which is sort of the default in the field, let's say, or like a standard approach in the field. And we start by evaluating marginal aspects, so sort of location-wise, and see that, okay, we have our bimodal temperature distribution here, and while the raw climate model has a significant sort of cold bias, which we can already see, both bias correction methods correct that, but we can see that they potentially introduce a slight warm bias. So this is again only looking at temperature. We can sort of look at this the distribution. So we plotted here the bias of the mean, the bias of the 10th percentile, and the 90th percentile, and see that whereas the raw climate model in blue has sort of overestimates the mean slightly, both sort of corrected climate models underestimated slightly, similar for the 10th percentile. And whereas we see that the mean sort of bias of the 90th percentile is around 0 for the raw climate model, we actually see that additional bias was introduced in the debiased climate models. So we're currently running this on testing data because it's just easier to sort of experiment with and change code. So this spatial distribution isn't as interesting yet because we're only looking at 4 grid points, but still we can here sort of see, okay, is there a certain region where the bias seems to be particularly large? And this might indicate, for example, something like a mountain range that's not resolved properly by the climate model. So this is an evaluation metric that can give the user a hint that there maybe is a problem with the underlying climate model driving this, driving all of these debiases. And again, we see that both bias correction methods introduce a slight cold bias. Then one approach we would like to show is sort of exceedance over threshold analysis. For a lot of impact studies, there's some sort of critical thresholds that are of interest. For example, nights below 0 degrees or something like that. So we implemented an approach where we try to understand whether the model reproduces the clustering and the frequency of exceedance of that threshold in different time periods. So here again, we see sort of the bias in the distribution of mean, the distribution of mean bias. So that's over the entire spatial area. And we see that both bias correction methods introduce or correct the bias, but introduce a slightly different bias. And here again, we can look at the spatial distribution of that error, and also evaluate the clustering, like I said. So here we, for one, look at the temporal clustering. So for example, the spell length of particularly hot days, which is of interest when studying droughts and heat waves, and see that the spell length in observations for particularly high temperatures is lower than for all of the bias corrected climate models. And for example, when looking at the spatial temporal clustering, we see that the ECMAP corrected version has a slightly longer tail than other bias correction methods. And like we said, one important thing to showcase the user so that the user can make an informed decision is to understand whether the method preserves the trend of the climate model. Like I said earlier, it's not necessarily the case that the climate model trend is credible. It's just that it's sort of a decision on the side of the user that needs to be made whether or not to correct this trend. So this was just sort of a brief overview of what we've done so far. And what we're planning to do is in the next weeks is develop or write more documentation and develop sort of a proper tutorial guiding the user through the package, implement more different evaluation metrics, and possibly also implement more different debiases, so that at the end we really have a package where the user can sort of experiment with different bias correction methodologies, see which one fits their use case best, also see the caveats of their respective choice, and make an informed decision. Thank you.
Okay, thank you, Fiona, and thank you, Jacob, for this great presentation. And this will be a super useful Python package, and I can't wait that it is published. So again, also the question to you, how challenging were the first 2 months for you developing this package?
Jacob, do you want to go ahead first? I can. Or...
No, you do.
Okay, so first of all, I also like the previous speakers, I want to say that I really want to thank our mentors, because I really I think we both really enjoyed the collaboration so far, and they were sort of gave input where needed and everything. So that was really great. I think I would say that the last months were quite challenging, and for me personally, sort of the main issue was with wrapping my head around bias correction as sort of a necessary, something necessary we need to do before conducting impact studies, but something that is also flawed in so many different ways, and sort of finding a way through this evaluation framework to make assumption transparent, and sort of we went through a lot of different iterations on that side to sort of understand, like, what does it actually mean to be trend preserving, and what does the user need to see. So I think there were a lot of conceptual challenges, but I also felt like I learned a lot, and I also learned a lot on because this is sort of the first time, at least for me, coding a full software package. So I learned a lot on that side as well.
Jacob, do you have something additionally to say, or also you would like to share your perspective?
I don't think I have much to add to that, honestly. I think we went through a lot of iterations on how to conceptualize, for example, the evaluation framework. I think a lot of the challenge also in the first months were kind of on the technical side. How do we implement what's kind of the software architecture? How do we implement user interface? Yeah, I feel like with the help of the mentors, we went through that quite well, and I'm excited for the next 1.5 months.
Okay, so we have one question on Slido. So thank you for the interesting presentation and the demo, Fiona and Jacob. Will the Jupyter notebooks be made available as well?
Of course. Yes, so
No, go ahead.
No, sorry, I didn't want to jump, so we're working with Jupyter notebooks at the moment, and we'll make the Jupyter notebooks available, probably maybe in sort of an enhanced version as well, so that it's really like a tutorial for users.
That's great. Okay, thank you again, Fiona and Jacob, for also being with us today during this midterm webinar, and looking forward to the final results then in September. So now I would like to invite Mohit, Anand, Emiliana, Miftari, Beatrice Rinaldi, and not sure if Engshi Sulkia could also join us today, but at least the first three, Mohit, Emiliana, and Beatrice, are today with us here. And they're working on a project, it's called CW for Floods, and it uses groundwater data, which is collected by citizens to improve flood forecasting. And how they do it, they will share this with us now. And so, yeah, Mohit, Emiliana, and Beatrice, and Engshi, the floor is yours.
Hi. Engshi will not be able to be here, but I will present the, can I share my screen? So,
yes, please.
Thank you. So we are going to, oh, sorry. Okay, so we are going to, our project is called Flood Forecasting. So we want to use citizen science to improve flood forecasting models. The Crowdwater project is a collection of hydrological data made by citizens, and we have the earliest data in February 2017. In this data, we have a lot of information about water quantity, water quality, like for example, the color of the river, of the water, about pollution, if there is plastic on the river and what kind of plastic and something like that. We have some stream information, like for example, the width of the river, and also a lot of images that citizens took of each station. The data that we want to use for our project, what is our project? We want to make use of this Crowdwater data to improve flood forecasting models in those stations, in those rivers that has not real gauging stations, real gauging data. And so we can help flood awareness. So the kind of data that we are going to use is the European Flood Awareness System, that is a pan-European domain. And the EFAS has a resolution, a spatial resolution of 5 by 5 kilometers. And it is an EPSG 3035 as a coordinate reference system, a Lambert azimuthal equal area coordinate reference system. And we have a temporary resolution of 6 hours. As you can see in the image, you can see the region of the EFAS domain. And then we have the Crowdwater data. We have a CSV file with 51 columns where we have a lot of different information, as I said before. So we have the day and the time in which the citizen scientists took the picture or the information. We have water level on virtual scale, as you can see in the image here in the right, and we are going to see this in detail later. Latitude, longitude of each station, and the route ID, that is the identification of each station. And then we have images. We have one image for each station in which we have the virtual scale, and multiple images after that without the virtual scale. So the first thing we did was cleaning the Crowdwater data. So we selected some relevant columns for a project, like for example, the virtual scale, latitude, longitude, day and time. We removed, there were a lot of rows with null or empty values, so we removed them. And also we removed the station that had only one observation, because we wanted at least 2 observations for each station to have something to compare. Since the Crowdwater project is worldwide, we concentrated mostly on the EFAS region, and so we removed all the stations that were outside the EFAS region, so the pan-European domain. And then the last thing we did was transforming the values of the virtual scale. As we saw before, they were text like -1, +3, and so on, and we transformed them in numbers that we could actually use. We selected a number of usable stations, and we had, for example, 367 stations with 2 or more readings, but still 2 readings were too little for our project. So we decided to get at least 15 or more readings per station. So at the end, we had 50 stations in the EFAS region. So the problem with the virtual scale, when we selected the stations that we wanted to use, we needed to understand what the virtual scale means, because this is not actually what is the meaning of a +1 in this scale, and what is the meaning of the -2? Is it the bottom of the stream or not? We don't know that. We only know that the 0 is the level of the surface water. We had other problems, like for example, these virtual scales didn't mean the same thing across different locations. As you can see, this scale is bigger than this one. So a +1 here is different from a +1 there. Another problem that we had is sometimes in some stations, these virtual scales were really big, really not representative of the actual water level. So even if we had a water level variation here, the measure will always be almost 0 because this +1 is too big to measure this variation. Or at least, even if we imagine that the water level may reach level 7, it seems something like a little bit apocalyptic. So it's not really representative of what happens in this river. So we didn't have only the pictures with the virtual scale. There was only one picture with the virtual scale for each station. We had a lot of other pictures like this for each station in different days, in different times, but still understanding the water level variation, it's not easy only from the picture. We wanted to try to use those pictures, and so we concentrated more on the virtual scale, on the picture with the virtual scale. And we came up with different proposals. We checked machine learning to use with the pictures, but actually we don't have so many pictures, so it was difficult to apply. And then we read some interesting papers about forensic photogrammetry in which they estimated the height of the suspects from CCTV frameworks. But still it was not applicable to our project because the images were completely different from the ones that they used in forensic photogrammetry or as orthophotos, for example, transforming the pictures in something in which we can take pictures on, in which we can take measures on. So we stick to the third method, that is the manual estimation. So the 4 of us just looked at the first picture of the 50 stations that we chose at the beginning. And from some objects that we have in the background, we try to estimate manually the amount in centimeters of this step. So for example, this seems to be a solar panel that might be 2 meters. And so I go there and say, oh, well, a +1 might be 80 centimeters. That maybe is too big, but we have 4 values and we could also remove outliers, for example. The same thing in this picture there. So we can say that this pole is 2 meters and each step might be 6 centimeters and so on. So each one of us made this estimation for each of the 49 stations because one station has no virtual scale, so we couldn't actually use it. And we estimated the virtual scale height. As you can see, we have a lot of different values. Sometimes the values are really equal to each other. Sometimes they are really big or really small. So we had to choose some station and to remove them. So for example, we computed the mean of the 4 heights for each station. We already removed the station that had really different values. And so we got at the end only 38 stations and not 50. But still, the mean of the 4 values didn't seem to us so representative of the actual value of each step of the virtual scale. So we decided to compute another mean after removing the outlier for some stations. Like, for example, this station here, the 4th station, it has 3 really equal values and 1 outlier. So we removed that and computed the mean between those 3. Sometimes they were all 4 really similar, so we kept all 4. And we did this manually because each station was different. So this is a comparison between the two mean. We selected the red one, the one in which we removed the outliers. And then what we did was using those values to substitute the virtual scale that we had at the beginning. And this was really helpful. One, because we had something in the metric system. The other one is because we can compare different stations. For example, these two stations here. And that was a really big thing for us, because at the beginning we couldn't compare the stations because the virtual scales were different from station to station. So what we want to do now is creating a general equation by learning the parameters of this equation using real gauging data and some extra information that we are going to get to use this general equation with the parameters in stations where we have only the water level variation from groundwater. Because there are a lot of small rivers in which we do not have real gauging stations with real data. And in those stations, the flood forecasting model might not be so good. Using the groundwater data that are taken in the station might be more useful to get better flood forecasting models. So then the extra infos, the next thing that we did was computing the width for the station, for the bigger rivers, and we used simply Google Maps and we just computed it in this way. For the smaller rivers, we actually had the values in the groundwater CSV file. And there are, and this is what we achieved so far. So we selected the groundwater stations. We converted the groundwater virtual values to standard metric in centimeters, and so we can compare the different stations. We computed the width of the river, and now what we want to do is using the digital elevation model of the regions in Europe to get the order of the river, the upstream area, the catchment, and then using different characteristics of the catchment, like the slope, the cross-section, like for example, saying that, let's say that the cross-section is trapezoidal, and so on. So, thank you.
Okay, thank you, Emiliana, for sharing, for this great presentation and also sharing your results so far. So it also shows again that using data from citizen science is quite challenging. I also have the question to you. So on a scale from 1 to 10, how challenging were the first 2 months for you working on this project?
Yeah, I can say a 7.5, 8, because yeah, the groundwater data were not so straightforward to use because there were a lot of uncertainties and we read a lot of literature, and so we lost a lot of time reading and trying to understand the groundwater project. And so I don't know if the others want to say something.
Same, even for me, like 8. I am on the average of 8.
Okay. Sorry, Beatrice, did you also want to say something?
Yes, I agree with Emiliana and Angie. It's very challenging, and the same to me, 8.5.
Okay, but yeah, I also hope that the learning curve is also steep, and but at the same time also gives you a lot of insights and new knowledge. We have one question on Slido. So do you estimate that the methods you employed and developed to clean up and correct the data could be used for other crowdsourced data?
Yes, I probably can answer that. Like, yeah, most probably yes, because we thought about a lot of things like going from photogrammetry, machine learning, and everything. But many at times, you even from the crowd water data, you don't have enough data, and you have many different kinds of errors. So what we did imply was more from the manual side, like we did the stuff ourselves, and then we took a kind of a majority voting kind of stuff to see what is the best that we could get, and these are very easily transferable to any kind of crowd water projects. Like, yes, they should be very easily employable everywhere.
Yeah, should be adaptive for each project, but yeah, are useful everywhere.
Okay, good. So this is quite promising also then for working in general with citizen science data. So thank you all for sharing your results so far and the great presentation today. And now we come to our last project that is part of this year's edition. It is implemented by Giovanni Paolini and Ainhoa Murillo Iraola. They unfortunately both can't be with us today, but they prepared a very nice recording about their work so far. And they work on a project with the title Wildfire Emissions Explorer. And this is an application that allows users to create plots of wildfire emissions with data on demand. And so, Ruben, I would like to ask you to start the recording for us, please. Right, and also, one of the mentors is also with us there. So if you have questions, so maybe Mark then can also respond to it. But now we first enjoy the video recording from Giovanni and Ainhoa.
Okay, the video is starting now.
Good morning, everybody. I'm Giovanni Paolini, and today I will show you our progress for the project Wildfire Emission Explorer, which is a challenge of the ECMWF Summer of Weather Code. But before diving into the details, I wanted to present our team. I am an aerospace engineer, currently doing a PhD in remote sensing in a company called ISARSAT, together with the University of Lleida in Spain. And Ainhoa, she's a mechanical engineer specialized in human factors, and currently covering the role of product owner at NICE Netherlands, and before also working as a UX UI designer in the same company. About the challenge, the general goal is to create an application that can retrieve a subset both in spatially and temporally of the big data set the ECMWF produced of wildfire emission. The dataset is the Global Fire Simulation System from ECMWF, and it is delivered daily at 0.1 degrees from 2003 until the present. It uses MODI, Ster and Aqua active fire products to assimilate in the GFAS. This dataset is then used from us to then extract a subset of data and visualize them in real time. To do this, we mainly used Python with these different packages. For visualization, we based our project on a Jupyter notebook compiled with Voila, so that it could be used as a web interface. And inside some packages used for visualization are also Leaflet and IPython widgets and IPython Leaflet, together with Matplotlib for the final plots. In the background, and then for processing, we used PostGIS to store all the data in the database and to query them, and then pandas and GeoPandas in Python to organize these queries and to visualize them. This is a prototype of well, now I will redirect you to the prototype that we've been developing, and the state at this moment. So there are different steps that the user is asked to do in order to finally retrieve the data from the dataset. First, is asked to retrieve a subset, a spatial subset, so to do a geographical selection of the area of interest globally. So you can choose from the different countries that are here selected when I hover on top of them, or to directly write the continent of the country of interest. For example, here in South America, I will select the South American area. Then there are also other interaction buttons that we developed. For example, we could draw a rectangle or a polygon, or the two of them together to select an area, and then combine them with also different countries. And finally merge all of them together in a final area of interest. This area of interest can then be downloaded to be reused on a second time with this upload button. So we developed some interface to make it easy to reproduce the same work more than once. Then after the geographical selection, in this case we choose a wide area in Europe, we move into temporal selection of the specific period we want to analyze. In this case, I selected the month of June of this year with a daily resolution. It could also be monthly in this, and with aggregation, with a special aggregation sum. So it will sum all the data inside the area of interest. Then as an optional choice, it's also possible to select a reference period to compare it with our period of interest to see what is the trend and what are the changes. In this case, since the dataset starts in 2003, I selected all the years until 2021. And then we can have a look at all the variables that is possible to query from the dataset. Usually the most used one is the wildfire radiative power. So here I select it. And finally, there are some plots that could be produced from this GUI. Like line, bars, and 2D visualization, and also animation. For example, bar plot will create both a visualization at daily scale of all the emission in the area of interest, sum them up together. So here is extracting the data for the specific period, the reference period, and now we finished. And here you can see what are in red the emission of the month of June of this year, and in gray of the previous years. We can also download this data into a CSV, and we will have the same numbers that we see here. So this is for the bar plot. It's also possible to create lines, and in this case it will extract it again. Pressing the same plot, it will create it. Also 2D visualization, where we see the area that we selected and the distribution of the wildfires, and also an animation. And here you see it's extracting data for all the days in June 2022, and it's possible to see the evolution of the fires in the area. So, and it's also possible to download the data daily for these plots to be able to reproduce them. So finally, after creating this GUI, we were able to have a first validation of the way we create this visualization. And to do this, we used the latest press release from ECMWF, where there is some data depicted for Alaska and for the latest wildfires in the month of June. And here you can see that the specific period of June of this year compared to the previous, the month of June of the previous years has a much higher value in terms of total fire radiative power. So we wanted to see if we were also able to reproduce this data, and we used the GUI to select the area of interest and the time period. And we finally created this bar plot, which has the same values as the previous one, and 2D visualization and the animation, where you can see that late in the month the wildfires are increasing sharply in the area, everywhere in Alaska. So this is the point we reach at the moment. We want to continue to add more plots and more and to make it easier for the interaction in the GUI, but this is already a working prototype, so we wanted to show you how it's been developed at the moment. If you have any question, I think our mentors can very well address them. I couldn't connect today, not me nor Ainhoa, but we will be there for the final presentation days. So thank you again, and see you in September.
Okay, so the last words from Giovanni were exactly also our next steps in the ECMWF Summer of Weather Code. So there is another 1.5 months for the 6 projects to continue their work and also to improve the results they already showed today. And then we will, I just share my screens. Oh, actually, I saw there is a question, and maybe Mark can respond to it if he's still here. So if it's possible to use different projections for the maps.
My video. Yeah, so I think we haven't got that to that stage, but I think given that they're using pandas, GeoPandas, and the usual sort of tools, it should be possible to change the projection. But I think most of the work has been in developing the means for rapidly querying the full data set to be able to produce the climatology, which is shown in the gray bar, and that's been like the major progress. So I think the rest is just details, but I think it should all be possible.
Okay, so thank you, Mark, for representing the team today on behalf of Giovanni and Ainhoa. And I just share my screen quickly. Okay, so the next steps for this year's ECMWF Summer of Weather Code edition is basically the next 1.5 months still coding phase until the end of August to finalize the projects, to improve and to continue the work that has been shown today. And then it is planned for now on the 28th of September, we will have the final ESOC day, which is a closure of the program where we also celebrate the outcomes from the projects, and where all the teams are again invited to present their final project results. And after 2 years of an online format of this final ESOC day, we are happy to organize or to have this final ESOC day this year as a hybrid version. So there will be an in-person component in Bonn, where also the mentors and the participants of ESOC this year will also be able to meet. But as I said, there is a hybrid format, so feel free also to join online to also follow the progress of the teams of the teams and also the final results then. So thank you so much for joining today. It was quite a long session, and I also don't want to take any more time. Again, it is about open source development, so feel free to also go on our website, esoc.ecmwf.int, to follow the progress and also to get more information about the final ESOC day. So if there is a way to register, then it will be certainly published on the website. And also please go to GitHub and have a look to the challenges or to the projects and also the project developments. There are a lot of demos and Jupyter notebooks and so on already shown today. And so GitHub is also a good way to engage with the teams in case you have some questions or you're also interested in using some of these outcomes. So thank you again for joining today. And I hope that I see or that you will be able to also join for the final ESOC day, which for now is planned to be on the 28th of September. Thank you and have a nice remaining day. Goodbye.